system, and I'm going to try to model it through this fractional diffusion equation. So this work is mainly done with my guide Abhishek there and Cedric. So in the previous talk, you have already heard about some of the stochastic models. So Priyanka had already introduced, but I'm still going to introduce again this model. So this model consists of a chain of particles in one dimension, and they are coupled to each other with a spring which is harmonic in nature, and the leftmost particle is connected to a heat bath, Langeva bath, which keeps this particle's temperature at a temperature of T left, and the rightmost particle is connected to TR. So the momentum square of this particle is TR, and the momentum square is TL at all times. So this system was introduced by Vasil, Bernardin and Ola in 2006, and and they have been studied after that extensively. So we studied the system in the open boundary and fixed boundary conditions. So the equations of motions are given something like this. So, and if there was no, if this system was only this, then the system is integrable because it's harmonic, and but in addition, so it has macroscopic number of conservation laws. But here we consider, to break this, we consider additionally a stochastic noise in the system, where the momentum is exchanged with the nearest neighbor. So with rate gamma at Poisson time. So apart from the Hamiltonian dynamics that goes on in the system, after some Poisson times, the momentum of the say into particles are exchanged randomly like this. So doing this brings the system to breaks the conservation laws for the higher conservation laws, and it only conserves the total like the stretch momentum and the energy in a closed system. And in an open system, you can in an open system they would be conserved in the bulk. So without exchange, that is, if the system is integrable, so if you put the two temperature profile temperature at this two end, the temperature profile comes out to be flat, and it's just the temperature is just TL plus TR by 2. But once you have the exchange and it breaks the higher conservation laws, the temperature profile shows some nonlinear behavior, which you have seen at a glance in the previous talk. So, so this model was exactly studied by Lepri, Monastery of Polity in 2009, where they have found through similar techniques as you saw in the previous talk, the steady state solution of the temperature and the correlations. And in a latter paper in 2010, they also write down equations of the evolution of temperature profile, and they compute the spectrum of the matrices, and comments that they are similar. The spectrum is similar to like shows some kind of characteristics of fractional diffusion. But after that, they didn't compute much. So in the latter paper, in this paper, Zara and Ola in 2015, they show that the energy evolution in a macroscopic scale for an infinite system is governed by this fractional diffusion equation, where this is the temperature field, and this is delta is the Laplacian, and to the power 3/4. If it was totally diffusive, then this 3/4 would have been 1.
Where does 3/4 come?
Where does 3/4 come? Okay, I mean, this is related to like the Levy process.
Yeah. Why is 3/4 the particular exponent?
Because, okay, so doing this microscopic thing, you can show that the energy diffusion is Levy 3/2, so the corresponding kind of this thing. So So what if we simulate this, the microscopic dynamics as described by this equation of motion in a computer, and if we study the temperature profile, so this red curve is a simulation data for for a system size of 126, and this green curve is a prediction that is made that is given in this paper, where this solution is basically given in terms of series, which I will come later. So you see that this prediction matches quite good. So this now what if we ask the question that if we start from a temperature profile which is initially say TL to the from 0 to say half of the system, this is scaled by n. So half of the system has been equilibrated at temperature TL, and the rest half is TR, and ask and let the system evolve with Hamiltonian dynamics. So so we know at time infinity it will reach a steady state which is like this, and we ask the question how does it evolve in time. And if you look at some intermediate times, you will typically see a profile which is not typically, I mean you will see a profile which is evolving something like this. So the question is that can we understand this evolution through starting from this is some kind of equation like this. So here in this thing we have plotted this temperature profile as scaled with x to the power n. So this is system. So there is some finite size effect which as they increase n there is some difference. So it was proven by so we can extend this definition of fractional Laplacian to a finite domain naively, and this is based on some unpublished work by Bessel and Ola. So now we say that the temperature of profile is governed by this equation. With now we want to solve it with some boundary conditions, which is at T0 at all times the temperature is kept constant with TL, and the other end is kept constant at TR. So we want to solve this equation in a time dependent manner. So how do we do that? So the question is, how do we solve this equation? So we take a hint from the normal diffusion equation. So in normal diffusion, the temperature is evolving like something like this, and in order to solve the time dependent equation, what we have to do is we have to write the equations for the temperature minus the steady state. And suppose if we have something like this and the steady state, and so we have to subtract this this two profile, and then say that, and this profile now satisfy zero Dirichlet boundary condition, and say that and then the time evolution of this profile is basically can be written in like evolving each of the Fourier components of this this function in the eigenbasis of zero Dirichlet boundary condition. So in case of diffusion, so if this is the case, then we expand it in sign basis, and the evolution, so ANs are found by Fourier decomposing the initial profile. Initial profile means t minus t infinity, and doing a Fourier and then evolving it in time as this eigenvalues of the Laplacian. So we can naively expect that like what if this is true for even the fractional diffusion. So this is based on some more, this can be said probably more rigorously by the work of Stefano Ola and others. So now we expect this for fractional diffusion. So So naively expect that this theta function, which is the steady state subtracted form, satisfies the equation something like this, where the thetas are zeros and boundary. So the question now is how do we construct an eigenbasis for this fractional operator, which is non-local, as Eli said, with zero Dirichlet boundary condition. So taking a hint from the temperature profile, which is solved exactly from Lepre, by Lepre, the temperature profile is given in a series form of something like this, which is this cosine series with lambda, this n pi to the power 3 by 2. Now, in steady state, if we have an operator which acts on this temperature profile, in steady state it should give you 0, and from there you can define an operation of this operator in this basis, which is cos n pi x, and you can define your operation something like this. So the fractional Laplacian, which is fractional Laplacian acting on cos, the eigenvalues are for the zero Neumann boundary condition are just n pi to the power 3 by 2, which is, if it was just Laplacian, it would have been n pi whole square. So, and this is phi n. Phi n's are like this complete basis between 0 and 1. So, given this definition, the question is, we can ask for a solution of this operator in some other basis, which is psi n, and where the psi n satisfy the boundary condition, which is 0 at 0 and 1, they are 0. And now we can express, we know the operation of this operator on phi n. We can express this psi n in terms of phi n, and then kind of uniquely get equations for the eigenvalues mu n and psi n. So mu n now is given by a solution of transcendental equation, and psi n can be computed from there. So once we compute, now this has to be found numerically. So we can find them numerically, and in the next slide I will show how they look typically. So what I plot here is this eigenvalues of this operator, fractional operator with zero Dirichlet boundary condition, and this is the eigenvalue spectrum. So as I increase n, so this orange dots are n pi to the power 3 by 2, which is the straight line, and this mu n are the numerical solutions with zero Dirichlet boundary condition, and at very large n, you see they coincide. So at large n, the eigenvalues of the Dirichlet boundary condition and the Neumann boundary condition are basically same, but for small values of n, they have some difference. And now from this you can compute the eigenvectors of the system. So what I plot here is the psi 1, which is the first eigenvector for the fractional Laplacian with Dirichlet boundary condition. So this black curve is the corresponding sine function. If it was Laplacian, then it would have been this curve for the zero Dirichlet boundary condition, the wave function for zero Dirichlet boundary. But here we see, if we construct psi 1, it's something different, and there's some kind of discontinuity in the wave functions at the boundaries. So, and then the next eigenvectors are basically somewhat similar, and they show considerable deviation from the corresponding sine functions. So, but as you increase n, they basically converge to, so this is the 20th eigenvector. So they basically collapse to kind of the sine function. So for large n, the eigenvectors are basically the sine functions, but for small n, they have some difference. So now we can kind of naively do, not naively, I mean, there's some rigorous proof, but we can expand, like expect that that theta function can be expanded. The time evolution of the theta function can be expanded in a series form like this, where like as in diffusion. So this theta n0 is found from the initial boundary, function with zero Dirichlet boundary condition, and it's expanded in this new basis which is psi n, and the temperature evolution is basically e to the power minus mu nt. If it was diffusive case, then this would have been mu n would be n pi square, and psi n are the sine functions. So psi n are defined by the wave functions. They're fixed by that they are zero at boundaries. No, psi always theta is now yes. I have subtracted the steady state solution.
So typically for fractional Laplacian, you need the complement to be defined, not just the boundary point.
Complementing.
I'm not understanding something. If you have a Dirichlet problem for the fractional Laplacian, the boundary value should be on the entire complement, not just the boundary. It's not a well-posed problem because the operator is not local.
Yes.
You mean that on 1 is infinity 0 is 0 and 1 is infinity 0?
But this is like this is defining fractional Laplacian in a finite too. So everything is between 0 and 1. So okay, this is I mean this might seem a bit ad hoc, but as I'll show that it matches with simulation, so come true. So now these two functions are basically satisfying. They are 0 at all times, and that like it's a similar construction of from Laplacian. So now what we do is now we start from an initial condition in the first picture that I show, that it's TL in the left half and TR in the right half. And then you find the Fourier decomposition of this initial profile minus the steady state in this basis, and because this is now a complete basis, and then evolve in time with this thing. And what I'll do is that we'll do this analytical solution and also compare with the exact numerical simulations of the original Hamiltonian. So what we see here is like the same curve as in the third slide. So this what I plot here is this black curves are the analytical like the solutions of those by doing this thing, and then you also add the initial the steady state profile, and this is for so what you need to really do is that you need to plot it for different scaled times. So as you increase system size, the time scales as like n to the power 3/2. So for this model, so you need to scale t by n to the power 3/2. And if you do this evolution, you can see that it's very good agreement with the simulation. So this is like they're totally different procedures. Like this is from this this red and the blue curves are from simulation. So also there is some finite size effect. So as you can see here, the blue curve is okay. It's not visible properly. The blue curve is more like it's almost over the black curve. So here there are some differences, but I believe that this is finite size effect. So as we increase system size, it will really, because this solution of the black curve really assumes that it's an infinite system, and then you do the solution. So it seems like so it seems that somehow it still works very good. So what what we are next trying to do is that, as you heard in the previous talk, there is another quantity model in which they have just two conserved quantity. As I mentioned here, that in this model there are like the three conserved quantities, which are stretch, momentum, and energy. And here in the other model which Priyanka described, they have the two conserved quantities, the energy and the stretch. There's no, so we are now trying to like see if this method works for the other case. Let's work with Anupam and Priyanka. So this is some separate. This is another work that I'm doing. So it's like in the same model, if you ask in equilibrium in the non-equilibrium steady state, and you want to calculate the fluctuations of in the non-equilibrium steady state, the fluctuations of energy. So so at time infinity, what you want to calculate is this the fluctuations of energy at site x and at site y minus the average value. So for the diffusive case, it was found by Cedric and in Lebowitz and Venkati that it is given by some kind of this is a work in progress. So this this is published. So it is given by the inverse of the Laplacian with the Dirichlet boundary condition, and it's given in series form. It's given something like this. So where delta T is the temperature difference between the two profiles. So if delta T is 0 and you subtract the same side correlation, which is T average square from fluctuation dissipation, and this is the long range correlations in the system. So we can ask the similar questions that what is this? Can we describe this long range correlations in this anomalous system using naively? If you expect that then extend this, then this definition goes back to is inverse of the Laplacian to the power 3/4. So we can compute this. We have the eigenvalues and the eigenvectors for this operator. We can compare with numerical simulations. So here we do that. So it's probably not very visible. So there is a black curve here. Okay, totally not visible. So there is a black curve here, and these are the numerical simulation data, and basically for different system size. But the problem is that like they match quite well, like qualitatively, but there is up to some scaling constant. So this is a work in progress. We are still trying to understand this thing. So basically, we want to figure out what kind of fluctuations we must add in order to produce a similar inverse to describe this long range correlations in this non-equilibrium steady state. But if you look at like numerically, I think there are two peaks which hit the boundary and then they of course reflect. But yes, they'll reflect, but those are for short times. So after that, you'll mostly the peaks vanish in the heat. There's a heat peak in the middle. So the amplitude, as Abhishek said, the amplitude of that is much smaller. So you probably doesn't matter.